Have you ever wondered if the start of a black hole and the start of the universe are actually the same physical concept? If they are indeed the same, then is our universe simply the interior of a black hole? If that is truly the case, then inside every black hole we know, is there an independent universe? Then how was the first black hole of our universe even born? This episode is quite hardcore, with a duration of 40 minutes. Hope it gives you a deeper insight. Among the billions of lights at night, finding it is no easy task. This region of space isn't dark, millions of stars illuminate it brightly. Their density there is hundreds of millions of times higher than the sky surrounding Earth. At this very center, a cluster of stars is spinning at an incredible speed. They all revolve around a strange, perfectly motionless point of light. This point of light is the orbital center for them and for every other star within the entire universe. And it is at the center that the body reveals its uniqueness. In the telescope's field of view, it isn't a smooth ring of light, but a massive, glowing ring. Below the ring's equator, it looks as if it were sliced. The center is a darkness deeper than the pitch-black space around it. As smart as you are, you surely know it's a black hole. But it's no ordinary black hole. This is the supermassive black hole at our galaxy's center, Sagittarius A star. At first, you might use the ship's power to fly toward this fellow. But it won't be long before an irresistible gravitational force starts pulling you toward it. You will find yourself involuntarily circling its waist, along with a glowing ring of matter being devoured by it. Under its powerful gravity, this matter is warped into a halo. In this accretion disk of matter, high-speed gases, dust, and various debris will knock you completely senseless. Intense friction makes the disk white-hot, releasing high-energy X-rays and gammas to continuously bombard your body. Your DNA would be long destroyed. Soon, however, that won't matter. Because at this very moment, your reality begins to turn eerie. From an observer's perspective, the closer you get to the disk, the slower you seem to fall. But to you personally, time passes just as usual. Only now, it's too late to escape. Everyone you've ever known, even their descendants generations later, are already figures of history. Not just time, but space is equally distorted. Suppose you fall feet first into that bottomless abyss. The gravity felt by your feet is far stronger than at your head. Your body begins to stretch and deform. Fortunately, for Sagittarius A*, a supermassive black hole, this effect isn't the most extreme. Compared to smaller stellar black holes, the tidal force of Sagittarius A* is actually quite gentle. This stretching will continue until, to an outside observer, it seems like a century has passed. After such a long time, your feet, then your waist, and finally your head, will cross that boundary called the event horizon. Once you cross this line, your time in this vast universe has come to an absolute end. Inside the event horizon, gravity is unimaginably strong. Not even light or any distress signal you might luckily send could ever hope to escape. You are forever disconnected from the world. Inside a black hole, all rules reverse. Time and space seem to swap roles. Inside the event horizon, time itself pushes you toward the center. No force in the universe can stop it, just as nothing can stop time from flowing. What you would actually experience inside, no one can say for sure. Of course, you couldn't say either. Even if you miraculously survived radiation, spaghettification, and the universe's aging, your voice would be forever suppressed. All that's left is the beast that ate you, its mass increased by a tiny bit. And this slight increase in mass helps it attract even more matter. This is the final fate of anyone or anything falling into a black hole. Since 1783, when someone first vaguely conceived of this concept, these ultimate cosmic predators, with their incomprehensible terror and mystery, have for decades captured the imagination of scientists, pushing the boundaries of science forward. In fact, scientists now generally believe that in the night sky, at the center of every galaxy, sits a supermassive black hole. They may even be the midwives to the birth of these galaxies. Though they sound like synonyms for destruction, these supermassive giants can sometimes feed and provide fuel, spawning the matter for stars, planets, and even life itself. But many of these supermassive black holes leave us with a massive question mark. How did they grow so big initially? If they are the seeds of galaxies, then what were their own seeds? And the universe's very first black hole, when exactly did it appear? And what did it look like? Where did black hole theory come from? It starts with Einstein's general relativity. In 1915, German physicist Karl Schwarzschild, even on the front lines of WWI, received Einstein's newly published paper on gravitational field equations. Impressively, he soon used Einstein's equations to provide the first exact solution. Schwarzschild's solution, simply put, describes a planet or a spherical object like a star, and how the surrounding space-time curves. He noted that if an object is small and dense, escaping its gravity would be extremely difficult. If you compress it small enough, within its Schwarzschild radius, the surrounding space-time would curve to the point where light cannot escape. The size of this Schwarzschild radius depends on the gravitational constant, light speed, and the object's mass. The greater the mass, the larger the radius. For example, Earth's Schwarzschild radius is about 9 millimeters, while the Sun's is 3 kilometers. Of course, because the actual sizes of the Earth and Sun are much larger than their Schwarzschild radii, we don't see any strange phenomena. Only when density is high enough does this extreme curvature appear. Unfortunately, Schwarzschild died of illness soon after, unable to see how his theory would later develop. At that time, many physicists doubted, did such incredibly dense bodies actually exist? Until 1964, when scientists used a rocket to send a Geiger counter into space. Just in the direction of Cygnus, a strong X-ray source was detected. The source was later named Cygnus X-1. The light from this X-ray source changes very rapidly, changing once in less than a second. This shows it's much smaller than an ordinary star. Later, by observing the orbit of its companion star, scientists calculated that the mass of Cygnus X-1 is about 15 times that of the Sun. This is much larger than the theoretical mass limit for white dwarfs or neutron stars. As a result, the light-swallowing singularity proposed by Schwarzschild became the most logical explanation. By the early 1970s, the secrets of Cygnus X-1 were gradually revealed. In 1967, American theoretical physicist John Wheeler, during a lecture, took the advice of an audience member and began using the term black hole to describe this completely collapsed gravitational body. The name was simple and vivid, and it quickly became popular. Now we have a fairly clear understanding of how stellar black holes are formed. When a star roughly 3 times the mass of the Sun runs out of fuel, the heat generated within it can no longer withstand its own massive gravity. It then begins a violent inward collapse. Most of the outer material is blown away in a spectacular supernova explosion, leaving only a highly dense remnant, surrounded by a boundary called the event horizon. Within the event horizon, Einstein's equations tell us time itself may be destroyed at the center point. Some even speculate it might lead to another universe. But these are still just conjectures, which cannot be verified through experiments. Scientists estimate that in our Milky Way galaxy, there could be about 100 million such stellar black holes. On April 10, 2019, a photo went viral globally. Honestly, from a visual standpoint, this photo isn't exactly stunning. It's blurry, just an orange ring of light on a black background. But behind this photo is the work of hundreds of scientists over more than half a century. Within just a few weeks, over 1 billion people saw this thing with their own eyes. Something physicists denied for many years, which most astronomers never dreamed they'd see with their own eyes. That's right. It's the first ever photo of a black hole. Black hole. From the name, you know it's pitch black. It doesn't emit light, so photographing one sounds like a fantasy at first. But scientists are very clever. They seized upon a feature of these gravitational bottomless pits, their greed and their influence on surrounding matter. Theoretically speaking, a black hole with enough mass, if surrounded by a vast swirl of gas and dust, called an accretion disk. Then, as the accretion disk is swallowed by the black hole, it becomes extremely hot due to intense friction and emits strong radiation in the form of high-frequency radio waves. This can then be detected by sensitive radio telescopes on Earth. To see them clearly, the black holes must be large. We're talking supermassive. Scientists call those with masses millions or even billions of times that of our Sun supermassive black holes. Astronomers believe these cosmic giants are lurking in the hearts of most large galaxies, perhaps even playing a vital role in the galaxy's formation and growth. They grow while devouring matter. Sometimes it even hiccups, spewing out chunks of accelerated gas. Strangely enough, these jet plumes can actually, as other celestial bodies perish, help new stars to form. The connection is so close that some astronomers began to ponder a chicken or the egg question. Did early galaxies nurture supermassive black holes, or did pre-existing supermassive black holes, in some way, seed the stars and galaxies that we see today? So, to find an ideal supermassive black hole to photograph, scientists first thought of our own, the center of the Milky Way. There lurks a supermassive black hole called Sagittarius A*, about 25,000 light-years from Earth, with a mass 4 million times that of the Sun. The advantage is it's relatively close, but it also brings some trouble. Because it's hidden in the Milky Way's bright, glittering star belt, too many celestial bodies block the way, making it hard to see clearly. Not only that, as the Earth rotates, the center of the Milky Way sweeps across the sky every night. It's hard for telescopes to lock onto it long enough to collect enough data. So this international team of scientists set their sights on a slightly more distant supermassive black hole. It is located in the Virgo cluster, at the center of the M87 galaxy. You might think it's strange, M87 is 55 million light-years away, much farther than Sagittarius A*'s distance. But it is massive enough. M87 is 6.5 billion times the mass of our Sun. Such size compensates for the distance. And at such a great distance, it appears relatively stable in the night sky, hardly moving at all. The line of sight is also clearer, with no obstructions along the way. Timing and location were secured. The next challenge was human effort, to build a telescope large enough to see M87's pitch-black core. In radio astronomy, the final image's clarity depends on the radio telescope's dish diameter. This means for small and distant targets, the bigger the telescope, the better. So, many modern high-resolution radio telescopes are named very directly. Like the giant Ukrainian radio telescope, the large millimeter telescope, the very large array, and so on. But for M87, the telescope size would need to be as large as the Earth. So researchers worldwide collaborated to link 8 radio telescopes distributed around the globe together, forming a virtual telescope with an equivalent aperture stretching from the South Pole to Spain. Its resolution is about 4,000 times higher than the Hubble Space Telescope. This behemoth, known as the Event Horizon Telescope, had its parts synchronized by atomic clocks. In 2017, for 4 consecutive days, it collected radio waves from M87. Because the data volume was so massive, network speeds couldn't handle it. So data from each observatory was delivered via physical hard drives. After 2 years of intense processing, the team finally obtained that seemingly impossible image, the silhouette of M87's event horizon, illuminated by radio light from its surrounding accretion disk. But the scientists didn't stop there. In May 2022, after another 3 years of processing, the Event Horizon Telescope's initial observations of our Milky Way were finally resolved, becoming the second black hole image in history. We've finally seen with our own eyes the beating heart we hold dear, Sagittarius A star. Photographing and analyzing these black holes is helping us understand these supermassive black holes and making continuous progress. But regarding their lifespan, especially how they were formed, there are still too many unsolved mysteries. How exactly does a black hole grow as large as M87, or even larger? Truthfully, 6.5 billion times the Sun's mass is nothing compared to the largest ones we've discovered so far. Ton 618 is a quasar located 10.4 billion light-years away, an incredibly bright celestial core. Its mass reaches a staggering 66 billion times that of our Sun. Scientists call it an ultramassive black hole. It alone is heavier than our entire Milky Way and all its stars combined. When matter around it is sucked in, it can reach 20% of the speed of light. It devours matter so fast that the light it emits is brighter than its entire galaxy and all the stars within it. So when astronomers detect these brightest objects in the cosmos, they are actually looking at these active galaxies and galactic centers, where supermassive or ultramassive black holes reside. They are arguably the most breathtaking single entities in the universe. But how did they form? Some believe these heavyweight contenders started out much like those stellar mass small black holes. A massive star reaches its end, dies a spectacular death, and leaves behind a large black hole. Then over billions of years, this gravitational giant gets lucky, encountering massive stars one by one, swallowing them to grow bit by bit, until reaching an unimaginable scale. It can even bind entire stellar systems firmly around itself, making them orbit it. But others feel that feeding bit by bit couldn't possibly make them grow this fast. They've proposed a different theory. They believe supermassive black holes don't just grow by devouring stars and gas, but are formed when several smaller stellar mass black holes collide and merge. In fact, scientists have detected the gravitational waves from such mergers, observing this phenomenon firsthand. This is surely a shortcut to gaining mass. But the question is, how often do two black holes actually collide like that? Perhaps continued observation of supermassive black holes near the Milky Way will help us find the answers. For now, it remains one of the greatest mysteries. When we point telescopes at the distant, and therefore very ancient universe, we still find supermassive black holes. The ultramassive black hole TON 618 is nearly 11 billion years old. Many other supermassive black holes were formed just millions of years after the Big Bang. Therefore, if they grew by slowly accumulating matter or through stellar mass black hole mergers time and time again, their appearance so early in the universe means that before they formed, countless stars had already been born and died to become their raw materials. But that's where the problem lies. Taking the mass of early supermassive black holes and combining it with accurate estimates of early star formation rates, the calculation shows that these supermassive black holes, they shouldn't even exist. Some giant black holes, less than a billion years after the Big Bang, already reached a billion times the Sun's mass. But theoretical calculations show that black holes formed at that time should be at most 100,000 times the Sun's mass. That's a massive 10,000-fold difference. There's also a phenomenon called direct collapse, which might explain some of it. These black holes weren't formed from the death of a star. Instead, just as the name suggests, massive amounts of matter in the early universe, even before any stars had formed, collapsed directly into black holes. These early, high-mass black holes could be what we see today as the infancy of supermassive black holes. But they might not be the final answer. Because their formation conditions are so strict, they are likely just an extremely rare phenomenon in the universe. Their numbers are too few to explain all the galaxies we see today, where every galaxy seems led by a supermassive black hole. So there must be some other key piece that we've missed. At the beginning of time, at the dawn of the universe, something must have existed, some kind of force, feeding these monsters from their very birth, helping them grow into the behemoths that drive our galaxies today. So, before the stars were even born, what exactly created black holes? Besides those formed by dying stars, are there other types in the universe? This brings us to Stephen Hawking. This great physicist, despite his lifelong battle with the challenges of ALS, made monumental contributions to cosmology and black hole theory. He changed how we see the universe's origins and the nature of black holes. Back in the early 1970s, Hawking described and defined basic rules for black holes, such as the event horizon, the boundary of that world, which once formed, only grows and never shrinks. Later, He even attempted to bridge Einstein's general relativity with mysterious quantum mechanics, two seemingly incompatible theories, to combine them. This led him to theorize a strange radiation. This radiation could actually cause a black hole to act like water vapor, slowly evaporating and eventually vanishing. This would later be known as Hawking radiation. Though it sounds perfect in theory, when it comes to actual observed black holes, we have never truly seen it. These were the puzzles Hawking spent his life exploring. Even while studying these deep, modern black hole mysteries, Hawking's mind often returned to the whole universe, especially the very moment it began. His research on black holes always provided new inspiration for his studies on the Big Bang. Conversely, his unique insight into the universe's first moments gave him a deeper understanding of black holes. So, in 1971, he boldly proposed an idea: at the dawn of the universe, a brand new type of black hole might exist. Called primordial black holes, they didn't come from the death of stars, but from the birth of the universe itself. Imagine 13.8 billion years ago, the Big Bang created energy fields everywhere. As the universe cooled and expanded, these fields gradually differentiated into the fundamental forces we know today. Cooling further, the first subatomic particles, like quarks and leptons, sprang out from that energy, endowed with fundamental properties such as mass and charge. These properties will, over the next 13.8 billion years, govern the physical laws of the universe. But the universe back then was still too small, too hot, and too chaotic. It was impossible for any of what we call real matter today to exist. Suddenly, driven by an unknown force, the universe underwent a process called inflation, a rapid expansion. In just about 1/10,000,000,000th of a second, its volume suddenly increased nearly 90 times. In that tiny universe before the expansion, minute fluctuations in quantum energy were amplified almost instantly into massive non-uniform regions on a cosmic scale. Throughout the post-inflation universe, everywhere, differences in particle and energy density appeared. These differences became, billions of years later, the seeds of the universe's large-scale structure. But Stephen Hawking also foresaw another result brought by these density differences after the universe's rapid expansion. We know that where there is matter, there is gravity. These higher density regions began, on a macroscopic scale, to warp space-time for the first time. To this sudden change, the universe's reaction was that those high-density regions began falling into gravitational pits of their own making. They collapsed inward due to gravity. The more they collapsed, the stronger their own gravity became. As this runaway gravitational collapse continued, the most fundamental materials of the universe were compressed into a mathematically infinitely dense point. This point would suck in everything around it, including photons that strayed too close. This point would be enclosed by an event horizon. Those newly born particles, before they had existed for even a second, were locked away forever. Thus, throughout the newly expanded universe, primordial black holes were born in the cores of the densest regions of primitive matter. Mathematically, only after the Big Bang, within a very, very brief window of time, roughly within the first second of the universe, could primordial black holes have formed. When the universe reached 1 second old, expansion and cooling had made it too large and too calm for gravitational singularities to spontaneously form. But before then, no physical reason could prevent primordial black holes from filling the infant universe. Hawking and other scientists calculated that within this 1 second window, the later the gravitational collapse occurred, the greater the mass of the resulting black hole. This meant they had a very wide mass range, as small as 1/100,000,000th the mass of a paperclip to as large as 100,000 times the sun's mass. But here lies the problem. As with much of Hawking's research, his beautiful mathematical derivations were flawless, but they left us with almost no way to verify them directly. How can we prove primordial black holes really exist, or do they not? We must find a way to detect them, or at least detect their actual impact on the early evolution of the universe. But when we don't even know how many there are, exactly when they were formed, or how large they specifically are, trying to find these earliest black holes is like trying to find a needle in the universe's massive haystack. Our solar system has 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Some planets, like Venus and Mars, were seen by the ancients with the naked eye thousands of years ago, while others like Uranus and Neptune. Malatuok Fat Hein Quoc In Vien Vong Sao Ne. Ho Si Boi Kak Na Koa Hak. Dau Tien Du Tren On Huang Trong Luke Len Tien The Kak. Masui Don Ra Su Tun Tai Qua Chung. Roi Sao Du Moi Tim Thay Chung 06 Tri Du Don. En Hung By At Dau Day. Trong He Mat Troi Van Con Mot. Han Tin Ma Chung Ta Chua Tim Thay. Du De Duok Hai In Q Han 4.000 Nam. Vu Tru Nai Truok Qua Na Chung Ta. Kung Van Con and Jo Kong It By Mat. Nam 1951, Na Tien Van Dai Hoc Chicago. Gerard Kuiper. Dung Hien and Gam Vemot Du La Lung Qua Sao Choi. Kak Na Koa Hoc De Fat Hein Sao Choi Chu Ky. Nan La En Hung Tienda. Chung Bon La En Hung Koi Bang. Di Chui En Trong He Mat Troi Voi Qui Deo Dai. Cu Moi 200 Nam Ho Si Nan Han. Se Type Can Trade Dat Va Mat Troi Mot Lan. 6 Du Nu Sao Choi Hali No Isheng. Lan Kui Tako The En In Thay Bang Mat Thuang. La Veo Nam 1986. Lan Toi Noki Lai La Koan Nam 2061. En Hung Han Tren Ne Qua No Se Kong. Type Dai Mai Mai. Moi Kai Sao Choi Den Gan Mat Troi. Fan Loi Bang Qua No Se Bok Hoi Mot Fan. Ki Them Vai Vong Nua. No Se Bien Mat Hon Ton Gi Yo Vu Tru Bao La. Si U Theo Dene. He Mat Troi De Tun Tai 4,5 Tai Nam. Dang Le Sao Choi Chu Ky Non Phi Du. Bok Hoi Het Sach Tu Lao Roi Moi Dung. Tru Kai Dung Nu Gerard Kuiper Sui Luan. Tai Vong Ria Qua He Mat Troi. Tuc La Noixa Koinig Y Qui Deo Sao Hai Vuong. Ko Mot K Huang Qua Kak Tien The Bang. Noi Du Ko The La Mot Van Dai De. Koi Bang Va Man Vun. En Hung Koi Bang Ne Ti Tho Ang Bai Sao Hai Vuong. Va Kak Han Tin Kong Lo Kak Gay En Hio Trong Luke. Bai De Ve Phi Mat Troi Roit Ro Ton Sao Choi. Bat Da Han Tren Tu Then Kio Dai Hangan. Tom Chi Hang Tri U Nam Qua Chung. Du Kuiper De Gi Nu Ve Tu Lao. En Hung Mai Den Nam 1992. Kak Na Koa Hok Moi. Tuk Su Tim Thay Van Dai Tien The Bang Ne. Bang Chung Ve Su Tun Tai. Du La Sao Kai Huang Ve Phi Nguai Sao Hai Vuong. Vung Kong Gien Vu Tru Duong Nu Trong Rong Du. De Tu Kan Kuok Tim Kim Kio Dai 5 Nam. Kak Na Koa Hok Nasa Dau Tien Fat Hein Mot. Sao Du Lan Logot Fat Hein Them Rat En Hio. En Hung Tien The Nu The Ne. Chung Duok Goi La Kak Tien The Nguai Sao Hai Vuong. Ku Vuk Chung Cu En Gu Duok Goi La Van Dai Kuiper. En Hung Kai Trong Van Dai Kuiper. Nai Kang En Hio Tien The Duok Tim Thay. Mot Chui En Ky La Kak Line A Sin. Han 6 Qua Vi Tien The Trong Rat Ky Quoc. 6 Du Nu Mot Han Tin Lun Ten La Sedna. Duok Fat Han Veo Nam 2003. Qui Deo Qua No Rat Dai Vacuc Ky Det. Ki Mot Von Quan Mat Troi Mat Han 10.000 Nam. En Hung Nai Ca Kai No Ogan Mat Troi Nhat. Koen Catch Gio and OVA Mat Troi. Van Gap 2,5 Lan Koen Catch 2 Sao Hai Vuong. Voi Koen Catch Xa Koi Nuve. Ti Trong Luke Qua. Sao Hai Vuong. Kong The Now De No Veo Qui Deo Lan Den The. Kong Ko Mot So Tien The Nguai Sao Hai Vuong. Voi Qui Deo Cucky Dac By At Kak. Qui Deo Qua Chung Kong Bo Hein Mot. Qui Luate Ky La. Du Hien Ve Kong Mot Phi Qua He Mat Troi. Han Nua Mat Fang Qui Deo So Voi Kak Han Tien. Ma Ta Quen Goi La Mat Fang Huang Deo. Lai Bin Hien Veo Kung Hien Trong. Zip Ve Mat Thong K. So Fan Bone La Cucky Koze Ra. Nu Kong Ko Nguai Luke Tak Dong. Qui Deo Qua Kak Tien The Ne. Dang Le Chi Trong Vong 100 Tri U Nam. De Ti Onen Han Lon Kong Hang Loi Roi. 6 Veo Nam 2012. Na Tien Van Brazil Rodney Gomez. Doi Voi Hein Tu Ong Qui Deo Ky Lane. De Du Ramot Loi Jatich. Ong Cho Rang Orian Nguai He Mat Troi. Tu Chat Con and Jo Mot Han Tin Xa Koi. Va Ko Koi Luong Veo Kong Kong Lo. Janu Mot Nuoi Chan Q. Am Tom Dan Dat Chui En Dong Qua Tien The No. Han Tin Kia Din Du. Sao Ne Duok Goi La Han Tin Thursday Chin. Du Tren Kak Tin Ton Qui Deo. Han Tin Ne. Planet 9's mass is about 6 times that of Earth. Its orbit is tilted, elongated, and elliptical. Its average distance from the Sunday is nearly 400 times Earth's distance from the Sun. But scientists used our most advanced telescope specifically to look for it, yet haven't found even a trace. Some skeptics say that Planet 9 might not exist at all. But there is a more imaginative possibility. This gravitational source possesses the characteristics calculated for Planet 9, such as mass, distance, and orbit. But it is something much smaller than a planet. And far more mysterious. What if it's a primordial black hole we haven't detected? Firstly, if we assume it's a black hole rather than a planet, it would explain why this gravitational source is so hard to find. An object with a mass of 6 Earths, if compressed into a black hole, its event horizon would only be about the size of a tennis ball. Not only is it pitch black itself, but against the vast background of the universe, it is simply too small. Of course, near our solar system, Hypothesizing primordial black holes is one thing. Actually detecting something so small, yet with such strong gravity, is quite another matter. Some believe their gravity could attract a small cloud of dark matter, forming a miniature halo around them. Just as galaxies are thought to be wrapped in a massive dark matter halo. So, if we look towards the direction where Planet 9 might be, to search for dark matter, and the radiation it might emit, maybe we could tell if it's a planet or a black hole. By the way, it could also provide evidence for early cosmic evolution. However, this method largely depends on our theoretical assumptions about dark matter. What exactly are its properties? These are questions scientists still haven't figured out. Dark matter is called dark matter precisely because it, though accounting for about 27% of the total matter in the universe, nearly 6 times more than the visible, tangible ordinary matter we know, but we have never directly detected it. To all the instruments we've invented, it remains invisible. Regarding what dark matter actually is, scientists mainly fall into 2 camps, respectively known as WIMPs and machos. Michael Wimp. WIMPs are thought to be subatomic particles, not in the standard model of particle physics. They interact with the universe only via gravity, while machos are considered massive, compact objects, existing within the universe. They might be what constitutes the dark matter halo, the dark matter surrounding galaxies, and causing gravitational effects. Stephen Hawking himself was one of the first scientists to predict that primordial black holes could be a type of macho. If that's the case, then a portion, or even all the missing mass in the universe, would be accounted for. The dark matter holding the universe together isn't just dark because we don't understand it yet, but because it is inherently black, composed of countless primordial black holes. These primordial black holes are like tiny pinholes in the fabric of space-time. When they cluster around galaxies, they use their collective gravity to control billions of stars. In the first second after the Big Bang, the total mass of primordial black holes formed might be enough to exceed all ordinary matter. Think about it. Of all the matter created at the dawn of the universe, perhaps only 1/6 escaped the fate of being immediately imprisoned within an event horizon. That is indeed a bit chilling. So how exactly do we detect a distant black hole? There is one approach that relies on another famous prediction by Hawking, Hawking radiation. Scientists believe that at the edge of every black hole's event horizon, when quantum particles interact under the massive gravity of general relativity, this radiation is produced. As a result, black holes emit a sort of gamma ray-like faint glimmer. And over time, much like water vapor, they slowly evaporate mass and shrink. Furthermore, Hawking also predicted the smaller a black hole's event horizon, the faster it evaporates. Eventually, this leads to an exponential release of energy and triggers a violent explosion. According to calculations, for any black hole with a mass less than 10 to the power of 11th kg, its lifespan should be shorter than the current age of the universe. Thus, we should be able to search the night sky for the gamma ray bursts emitted in their final moments. Starting from 2008, the Fermi Gamma Ray Space Telescope, orbiting Earth in low orbit, was perfectly suited for this mission. But unfortunately, after nearly 15 years of observation, the results are not optimistic. The key evidence or lack thereof is that we have barely observed the expected Hawking radiation bursts. Statistically speaking, this means that dark matter composed of these tiny primordial black holes might not even account for 1% of the total. Of course, there is also a possibility that Hawking's theoretical derivation, which tried to unify quantum mechanics and general relativity back then, went wrong somewhere. The so-called Hawking radiation and related bursts might actually not occur at all. After all, these conclusions are based on a series of complex mathematical derivations, with no highly reliable observational data to directly confirm them. As for other potential detection methods, they rely more on comparing traditional orbital mechanics with our actual observations. The Fermi Gamma Ray Space Telescope, besides searching for gamma rays possibly from primordial black holes, can also detect gamma rays from other celestial sources. For example, if those from pulsars or supernova explosions were to flicker unexpectedly during propagation, it could be because a primordial black hole just passed between it and us. Its gravity bends the light rays. This phenomenon is called gravitational lensing. Similarly, When a primordial black hole passes in front of an ordinary star, the light from the star may also be bent, causing the star's observed brightness and apparent size to change. However, the results of these methods are still not ideal. Whether in gamma-ray astronomy or optical astronomy, no convincing gravitational lensing events caused by passing primordial black holes have been found. Based on the duration of observations and statistical analysis of the number of suspected events, it provides an upper limit for the number of primordial black holes in specific mass ranges. Based on these results, scientists believe that distant black holes as small as Earth or smaller are highly unlikely to be the hidden machos that make up the bulk of dark matter. Scientists have also tried looking for clues from other angles, but with little success. Logically, those distant black holes wandering the universe should have enough gravity to capture other compact celestial bodies. For instance, neutron stars and white dwarfs would ultimately be devoured by them. But in reality, we observe that in the universe, there are still many neutron stars and white dwarfs. This, in turn, limits the number of primordial black holes that have existed over the past 13.8 billion years. Even if we look into the distant past of the universe, trying to find traces of these early phenomena, the results are still unsatisfactory. If primordial black holes had existed in large numbers shortly after the Big Bang, then in the early history of the universe, they would have started attacking surrounding matter. If this process happened early enough, it should have left recognizable signals in the distribution patterns of the cosmic microwave background radiation. However, scientists have analyzed these cosmic scale fingerprints in detail, and found no clear signs pointing to the existence of early black holes. At least for those between 100 to 10,000 times the Sun's mass, that is the case. If they truly existed, they were either too small or too few to leave a clear mark on the CMB. Ever since Stephen Hawking first proposed in 1971 that primordial black holes might exist, astronomers have been racking their brains trying to find ways to verify or disprove this hypothesis. For a long time, these efforts yielded no positive results. The prospects for primordial black hole theory once looked quite bleak. Until 2015, when things finally took a turn. That year, a massive new scientific facility in the US, the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves for the first time. Scientists traced the source of these waves and found they came from a black hole merger. The mass of each black hole was about 30 times that of the Sun. This discovery was exciting enough in itself. It not only confirmed that gravitational waves exist and can be detected by us, but also showed that they can serve as a powerful new tool for exploring the distant universe. But what excited black hole scientists even more was the deeper implication of this discovery. A black hole with 30 times the Sun's mass, if based on traditional stellar death and collapse theories, is very difficult to form. They are simply too large. But if explained using the mechanisms behind supermassive black holes, they appear too small. So, could there be another explanation? Primordial black holes might be the answer. If most primordial black hole masses fall within this range, then calculations based on their number and distribution show that their collision frequency seems to match LIGO's currently detected gravitational wave events. They align quite well. Finally, a measurable result seems to have revitalized this ancient black hole theory. Of course, previous observations that found no evidence did not entirely rule out primordial black holes' existence. They just set stricter limits on their possible mass range and quantity. These restrictions might make them unlikely to be the sole source of dark matter, but the debate over how they formed and the role they play in the universe is far from over. Current observational technology has yet to cover certain mass ranges, leaving some possibilities open. In fact, scientists have run computer simulations. If all hypothetical dark matter in the universe were replaced with primordial black holes about 1.4 times the mass of the Sun. Simulation results show that in the early evolution of the universe, they played a very important role. This includes serving as the first stars, the first galaxies, and the seeds of supermassive black holes. Whether primordial black holes were truly formed within the first second after the Big Bang, or when they formed, and how they evolved, these questions to this day remain one of cosmology's greatest mysteries. It is also a hot topic attracting various scientific speculations and experimental research. Scientists pin their hopes on the latest, most advanced observational instruments, such as the James Webb Space Telescope. It will capture images of the universe's earliest stars and galaxies, and attempt to verify theories about primordial black holes seeding the universe. Or the Laser Interferometer Space Antenna, LISA, the space gravitational wave detector planned for launch in the mid-2030s. It will be able to directly search for black holes potentially the size of primordial ones, via gravitational ripples from their mergers. Regarding the first black holes, we still have so much more to learn. But as Stephen Hawking realized, understanding them provides us with the chance to uncover the whole universe's mysteries. Primordial black holes may hold the key to unlocking the earliest secrets of our universe, the nature of dark matter, the force driving supermassive black hole growth, the evolution of stars and galaxies, and ultimately, the mystery of our own origins.